24 centimeters a year. That is the rate at which two of the planet's great tectonic plates are driving into each other beneath the Tonga-Kermadec Trench, the fastest plate convergence on Earth, moving nearly a hand's width every 12 months. In roughly 30 hours, this underwater collision zone fired off 6 earthquakes along a 2,000-kilometer line aimed directly at New Zealand. On a map, the sequence looked like a fuse burning south toward a populated mainland. But when you examine the exact data, and specifically a single measurement, that entire countdown narrative dissolves. The headlines frame these 6 events as a progressive chain reaction loading stress toward the South Island. That loose framing completely misinterprets the physics. What actually happened was a series of independent ruptures across vastly different depths on the world's most active subduction segment. Understanding why this line was not a migrating threat is a much better story than the panic, because it exposes the real machinery of deep Earth dynamics and highlights where the actual hazard lives. The central question this episode answers is simple. Why does a scatter of moderate ocean quakes look like a moving countdown? And what does the real seismic clock beneath New Zealand actually say? To see through the map illusion, you have to break down the events. The strongest shock of the sequence hit a magnitude 5.6 just after 1200 Coordinated Universal Time near the Kermadec Islands. The United States Geological Survey ran its automated impact assessment, and the system returned a green alert within minutes, confirming 0 estimated fatalities and no significant economic loss. Other events along the string included a magnitude 5.0 south of the Kermadecs, a magnitude 5.0 near Samoa, and a magnitude 4.6 south of Fiji. A separate magnitude 4.8 near Vanuatu was swept into the same news graphics, even though it occurred on an entirely different fault system thousands of kilometers away, a classic example of unrelated events being visually grouped into a single false narrative. The key that dismantles the countdown model comes down to depth. While the Kermadec and Samoa shocks occurred in the upper crust at depths around 10 kilometers along the shallow plate interface, a magnitude 4.9 shock north of Tonga struck at a depth of 114 kilometers. That event occurred deep inside the descending Pacific slab as it bent and tore under its own weight inside the mantle. A shallow interface quake and a deep intra-slab rupture cannot form a single propagating rupture front. They are independent events occurring on a boundary that routinely experiences massive stress. Just 4 months prior, in March 2026, this same boundary produced a massive magnitude 7.6 quake at a depth of 237 kilometers near Tonga. The strongest quake recorded anywhere on Earth in early 2026, yet it caused no tsunami and no damage due to its extreme depth. For North American viewers used to monitoring systems like the Queen Charlotte Fault off British Columbia or the Cascadia subduction zone stretching from Vancouver Island down into Oregon, the Tonga-Kermadec system represents the extreme upper limit of plate velocity. While Cascadia creeps along at roughly 4 centimeters per year, Tonga-Kermadec moves at 6 times that speed. 6 moderate quakes across 2,000 kilometers in 30 hours is not an escalation. For this specific trench, it is the background baseline. The true hazard to New Zealand is not being imported from Tonga. It is already built into its own geology. The Hikurangi subduction zone runs directly beneath the east coast of the North Island, while the South Island is bisected by the Alpine fault. Historical and geological records show the Alpine fault produces a major magnitude 8.0 earthquake roughly once every 300 years. The last major rupture occurred in the year 1717, meaning 309 years have elapsed. Published scientific estimates now place the probability of a major Alpine fault rupture within the next 50 years at approximately 75%. Moving forward, there are 3 specific markers on the watch list to determine if conditions are changing along this system. First, watch for any single shallow rupture exceeding magnitude 6.5 along the Kermadec segment, which is the threshold where local tsunami generation becomes a factor. Second, watch for formal advisory updates from Geonet or the United States Geological Survey regarding depth revisions on the Tonga intra-slab sequence. Third, monitor the frequency of slow slip events along the Hikurangi margin beneath the North Island. Until one of those specific thresholds is crossed, this 30-hour sequence remains what it has always been, the normal baseline hum of the fastest plate boundary on Earth. 2,000 kilometers of open ocean, 6 earthquakes in 30 hours, and not one of them was a foreshock to a major disaster. What social media maps portrayed as a migrating threat advancing south toward New Zealand was in reality a normal day on the most aggressive plate boundary on the surface of the planet. To understand why this 30-hour sequence was ordinary baseline behavior rather than an impending catastrophe, you have to look at how the Tonga-Kermadec Trench has operated throughout recorded seismic history. Most major plate boundaries around the Pacific Ring of Fire, including the Cascadia subduction zone off Vancouver Island or the Queen Charlotte Fault System farther north, converge or slide past each other at rates measured in millimeters or a few centimeters each year. Cascadia, for instance, locks and accumulates strain at roughly 4 centimeters per year. The Tonga-Kermadec boundary operates in a completely different category. At the northern end of this trench near Tonga, the Pacific Plate converges with the Australian Plate at a rate of up to 24 centimeters every year. That is roughly 9.5 inches of slip annually, making it the fastest documented plate convergence zone on Earth. Because the plates collide at nearly a hand's width per year, the mechanical stress built up along the interface must be released continuously. The baseline expectation for this system is not silence, it is perpetual high-energy deformation. Historically, this trench serves as an industrial factory for large seismic events. It regularly generates earthquakes above magnitude 8. Furthermore, because the ancient cold oceanic crust of the Pacific Plate plunges almost vertically down into the Earth's mantle, it remains cold and brittle enough to snap at extreme depths. While most global earthquakes are confined to the upper 30 kilometers of the crust, the Tonga-Kermadec slab routinely produces deep-focus earthquakes down to nearly 700 kilometers below the surface, nearing the boundary of the lower mantle. A clear demonstration of this baseline machinery occurred in March 2026. A massive magnitude 7.6 earthquake struck along this exact boundary near Tonga. Because the rupture occurred at a depth of 237 kilometers inside the descending slab, it displaced no ocean water and generated no destructive tsunami. Tonga issued a brief precautionary advisory and quickly lifted it. Even though that magnitude 7.6 event stood as the strongest earthquake recorded anywhere on Earth in early 2026, it passed without major destruction simply because of its depth. When you contrast that historical baseline against the recent 30-hour cluster, the scale becomes clear. The sequence included a shallow magnitude 5.6 shock in the Kermadec Islands at 10 kilometers depth, which triggered an immediate green rating from the United States Geological Survey, confirming no damage. It included magnitude 5.0 quakes near Samoa and the southern Kermadecs, a magnitude 4.6 south of Fiji, and a deep magnitude 4.9 event at 114 kilometers depth north of Tonga. Spread across 2,000 kilometers of trench, this activity represents the ordinary background noise of a system moving at 24 centimeters a year. The true seismic tension in the region does not depend on these moderate oceanic quakes. It resides in the southern continuation of the plate boundary beneath New Zealand, the Hikurangi subduction zone off the North Island, and the Alpine fault running down the South Island. Geological records show the Alpine fault ruptures in a major magnitude 8 earthquake on an average cycle of roughly 300 years. The last major rupture occurred in 1717, meaning 309 years have passed, placing the fault past its average recurrence window. Recent scientific studies estimate a 75% probability of a major Alpine fault rupture within the next 50 years. To monitor whether conditions on this broader system are actually shifting, watch for 3 checkable metrics. First, check for any shallow rupture along the Kermadec or Hikurangi segments exceeding magnitude 6.5, which marks the threshold for potential local tsunami evaluation. Second, watch for formal updates from the Geological Survey of Canada or Natural Resources Canada regarding Trans-Pacific tsunami monitoring if a major shallow event occurs. Third, monitor Geonet data for sudden changes in slow-slip tremor rates along the Hikurangi margin. Until those specific physical indicators change, this 30-hour cluster remains a stark demonstration of how a normal baseline on the world's fastest fault can easily be misread as a countdown. 114 kilometers straight down into the earth. That single depth figure is the precise physical barrier that breaks the narrative of a migrating seismic threat. When headlines warned that stress was marching south toward New Zealand, they assumed all 6 earthquakes in the sequence were operating on the same flat interface. But the mechanics of subduction zones are far more three-dimensional. To understand what actually broke during this 30-hour window, you have to look at the 2 distinct mechanisms driving seismic failure along a subduction trench. The first mechanism is shallow interface slipping. This occurs where the overriding plate, here the Australian plate, grinds directly against the top of the descending oceanic slab, the Pacific plate. Friction locks the 2 rock faces together until accumulated strain overcomes the strength of the fault, resulting in a sudden, shallow slip. The magnitude 5.6 earthquake near the Kermadec Islands at 10 kilometers depth and the magnitude 5.0 events near Samoa were shallow interface ruptures. If a sequence consists entirely of shallow interface events along a narrow line, stress transfer can theoretically nudge adjacent locked patches closer to failure over short distances. The second mechanism is intra-slab deformation, and this is where the simple countdown model completely fails. As the cold, heavy Pacific plate is forced beneath the Australian plate at 24 centimeters per year, it plunges steeply down into the hot, viscous rock of the mantle. The slab does not slide smoothly. Its own immense weight pulls it downward, causing the internal structure of the subducted plate to bend, stretch, and fracture internally. The magnitude 4.9 earthquake north of Tonga struck at a depth of 114 kilometers, roughly 95 miles below the surface. That rupture occurred entirely inside the body of the sinking oceanic slab, well after it had already been swallowed deep into the Earth's mantle. An intra-slab rupture is a fundamentally different physical process than a shallow interface quake. It is caused by internal stress tearing at the descending slab under gravity, not by the 2 outer plates slipping against each other. Because these 6 earthquakes were driven by completely separate physical processes occurring at wildly different depth horizons, they could not represent a continuous, single-file transfer of stress. There was no single main shock triggering a cascade down a fuse. Furthermore, physics sets strict limits on how far one earthquake can trigger another. Seismologists evaluate 2 types of stress changes: static stress transfer and dynamic triggering. Static stress transfer permanently shifts stress on neighboring faults, but its force drops off exponentially with distance, making its effect practically zero across hundreds or thousands of kilometers. Dynamic triggering occurs when transient seismic waves pass through distant rock formations. While massive megathrust events above magnitude 8.0 can dynamically trigger distant microseismicity, moderate magnitude 4 and 5 quakes simply do not release enough energy to dynamically trigger major ruptures thousands of kilometers away on New Zealand's Alpine fault or Hikurangi subduction zone. This mechanical breakdown confirms that the 30-hour cluster was simply a statistical alignment of independent events along an exceptionally fast 24 centimeter per year plate boundary. To monitor how stress actually behaves along this region, watch for 3 specific markers. First, monitor automated depth profiles published by the United States Geological Survey and Geonet to see if any new cluster isolates entirely within the shallow upper 10 kilometers of the interface. Second, watch whether ocean bottom pressure sensors managed by regional seafloor observatories detect any sudden vertical seafloor displacement. Third, watch for any formal hazard communications from Natural Resources Canada or global monitoring bodies regarding significant magnitude 7 or greater megathrust activity. Until those specific physical measurements indicate a change, the mechanism remains clear. A deep slab tearing under its own weight is not a fuse burning toward a mainland. 309 years of accumulated mechanical strain along a single fault scar. That is the real physical baseline hanging over New Zealand, not a 30-hour scatter of moderate ocean quakes 2,000 kilometers to the north. While headlines focused on 6 offshore earthquakes, the actual impact of seismic hazard in this part of the southern hemisphere is tied directly to local infrastructure and geography. The Tonga-Kermadec sequence, ranging from a shallow magnitude 5.6 in the Kermadec Islands down to a deep magnitude 4.9 north of Tonga, passed without damaging a single building or raising a tsunami alert. The United States Geological Survey System rapidly registered green impact assessments across the board. But shifting focus away from online mapping panics allows us to evaluate what a real rupture on this extended subduction system actually changes for communities on the ground. The Hikurangi subduction zone runs directly off the east coast of New Zealand's North Island, while the Alpine fault cuts across the South Island. When seismologists evaluate a magnitude 8.0 rupture along the Alpine fault, a recurring event with a historical average interval of 300 years, the impact translates into immediate physical consequences. A major strike along the Alpine fault would sever critical transportation arteries across the southern Alps, cutting off mountain passes, disrupting regional power grids, and isolating isolated coastal communities. For Canadian viewers, the scale of this exposure aligns closely with the risk along the Cascadia subduction zone off Vancouver Island or the Queen Charlotte Fault off Haida Gwaii. If Cascadia were to rupture in a megathrust event, last logged on January 26, 1700, the physical mechanisms would be identical. Severe ground shaking lasting several minutes, widespread infrastructure displacement, and local tsunami waves reaching coastal inlets within minutes. Natural Resources Canada monitors Cascadia using sensor arrays operated by Ocean Networks Canada, tracking episodic tremor and slip events to measure subtle strain accumulation. In New Zealand, Geonet serves that exact monitoring role along the Hikurangi margin. The distinction between real risk and internet alarm comes down to how infrastructure responds to baseline motion versus major ruptures. The Tonga-Kermadec boundary moves at 24 centimeters per year, nearly a hand's width every 12 months, releasing energy through frequent deep and offshore quakes that pass virtually unnoticed by daily commerce. Conversely, a locked fault line like the Alpine fault stores that energy silently over centuries. With a 75% probability of a major Alpine fault rupture estimated over the next 50 years, emergency management agencies are not planning for a distant migrating sequence. They are preparing for the sudden release of 3 centuries of built-up strain beneath their own feet. To determine how real-world risk develops over the coming months, keep your eyes on 3 specific data checkpoints. First, monitor official bulletins from Geonet for any recorded elevation changes or abnormal slow-slip tremor episodes along the Hikurangi margin. Second, watch for updates from the Canadian Hazards Information Service or the United States Geological Survey following any shallow Pacific Ocean rupture above magnitude 7.0. Third, track whether regional civil defense authorities issue new land use or building code revisions based on updated Alpine fault paleoseismic modeling. Until one of those verifiable metrics shifts, the reality remains unchanged. The 30-hour line of ocean quakes was the routine baseline of the world's fastest tectonic boundary, while the true seismic clock continues its quiet countdown directly beneath the mainland. 6 moderate earthquakes across 2,000 kilometers of ocean, and not a single millimeter of stress transferred to the fault that actually threatens New Zealand. When you strip away the dramatic red lines drawn across digital maps, what remains is an exercise in scientific precision versus online pattern recognition. What is clearly established by the observational data from the United States Geological Survey is that the 30-hour sequence was composed of independent ruptures across different depths and fault regimes. The shallow magnitude 5.6 in the Kermadec Islands, the magnitude 5.0 near Samoa, and the magnitude 4.6 south of Fiji occurred along the shallow plate boundary, while the magnitude 4.9 north of Tonga occurred 114 kilometers deep inside the subducting Pacific slab. Because these events involve different mechanical processes, separated by vast vertical and horizontal distances, they could not function as a single migrating fuse. What remains unresolved is the precise timing of when the southern extension of this tectonic system will ultimately release its stored energy. The Hikurangi subduction zone and the Alpine fault are loading stress continuously. The Alpine fault, having last ruptured in 1717, sits 309 years into a 300-year average cycle, with a calculated 75% probability of a major rupture within the next 50 years. Science cannot predict the exact day or hour of that failure, but it can confirm that 6 moderate ocean quakes 2,000 kilometers away did not alter its timeline. To follow this situation as it develops, keep these 3 specific checkable items on your watch list. First, watch whether any future seismic activity along the Kermadec Trench forms a concentrated swarm strictly within the upper 10 kilometers of the interface, rather than dispersing across deep intra-slab zones. Second, watch for formal seismic advisories issued by Geonet or the Canadian Hazards Information Service regarding abnormal crustal deformation along the North Island coast. Third, monitor global monitoring networks like the United States Geological Survey for any shallow Pacific megathrust event exceeding magnitude 7.0, which is the physical scale required to generate regional tsunami impacts. Until one of those specific developments occurs, the most likely situation is that the Tonga-Kermadec Trench is simply continuing its normal baseline hum at 24 centimeters per year, while the Alpine fault quietly accumulates strain on its own independent schedule. The ultimate takeaway is clear. The most dangerous fault line is rarely the one making headlines for a busy 30 hours, but the one that has remained silent for 300 years. Let us know in the comments where you are watching from today. If you value precise, data-driven analysis of real-world Earth systems, subscribe and hit the notification bell to catch our next investigation.